Last but not least, we're going to take a look at some symmetry in this lesson. By the end, I hope you can identify and describe symmetry in terms of geometric figures. So as a little bit of a warm-up, I want you to be able to take a look at these and recognize what kind of transformation happened to it. I think in the first one, you realize it's a rotation in order for it to match up like that. And with the second one, you almost picture a line right down the middle where it's like a mirror image, a reflection, in order for that to match up. That one actually might be a rotation as well in order to combine and make it look like that. We're going to go a little bit deeper in that idea. Two types of symmetry. There's line symmetry and rotational symmetry. A figure has symmetry or reflection symmetry if it can be reflected across a line so that the image coincides with the pre-image, so it matches up perfectly. The line of symmetry, also called the axis of symmetry, divides the figure into two congruent halves. So our heart here, that when reflected across that dotted line, it makes the identical image over here. So that's line symmetry. A figure has rotational symmetry, also known as radial symmetry, if it can be rotated about a point by an angle greater than 0 but less than 360 so that the image coincides with the pre-image. So when you're rotating it or turning it for it to match up, then it's showing that it has rotational symmetry. With these examples, we want to be able to tell whether the figure has line symmetry. If so, draw all the lines of symmetry and state how many there are. With this first image, I think you should be able to see, if we fold it right along there, right along there, we can fold it along here. These are all different ways that we can fold it in order to have it have the exact same image. Those four are the most common, but what if I told you that there's four more? You would have forgotten there, here, there, and here. So there's actually a total of 8. So yes, there's line symmetry, and then there's 8 different lines. When you get to number 2, I think you would recognize that there are no lines of symmetry. I can't draw on a line for it to reflect across and match up exactly. With number 3, I think you would agree, yes, I can fold it right there. I could fold it right there. And I'd also be able to right here and right here, having a total of 4. On number 4, I think you would agree that we're only going to have 1, and it's right there. Number 5, I think you would agree that there is. We can fold it right along here for it to match up, and then also right here. It might look like the diagonals could, but those don't match up, so that would only have 2. with number 6, the obvious look would be right here. Now, if you dig deeper, you notice with kind of how these stars are and these stars that it doesn't match up exact. But I think it's intended to actually have one line of symmetry. So if we're saying, if we're not counting the stars, then yes, there's definitely one. But I can understand your argument to say that there isn't. But I would want you to point out the idea with those stars, if that was the case. One last idea was the rotational symmetry. So the angle of rotational symmetry is the smallest angle through which a figure can be rotated to coincide with itself. So have it match up with itself. The number of times the figure matches up with itself as it rotates through 360 degrees is called the order. So it's tough to do this not in person, but on this first one, I guess if I'm looking at this side first, I can rotate it 90 degrees and this top part then matches up here. So that's like one order. It would rotate again, that part would end up matching up on the bottom now, 2, and then it would be on the side, 3, and then for the fourth one it would match up where it originally started. So in order to figure out what that degree was, you actually take 360 degrees divided by the order. So since it took 4 times to match up in order to get back to where it started, 360 divided by 4 gives us 90 degrees. And what that's going to be is the angle of rotational symmetry. If we take a look at the next set of examples, I think you would agree with number 1. There is no sort of angle of rotational symmetry there. With number 2, kind of looking at that part of the figure, if that rotates, kind of picture the middle is like that where it's turning, it would take 2 turns for it to match up exactly where it started from. So yes, it does have rotational symmetry, and we would take 360 divided by the 2 in order to say it has a 180 degree angle of rotational symmetry. With number 3, I think it clearly does. And how many times would it take to rotate? If I'm starting right here, it would then hit here 2, then hit here 3, all the way around for 4. So 360 divided by 4 would give us a 90 degree rotational symmetry. On the fourth one, if you're kind of looking, this would then rotate to hit here, to then rotate there, to then rotate back to the top. So 360 divided by the 3 gives us a 120 degree rotational symmetry. Number 5, it might be tougher to see, but if I rotated right through there, it would take 1 to hit this spot and then another one to hit the top. So 360 divided by 2 is 180 degrees. And then on number 6, we can't get that to rotate to match up with itself. As always, hopefully we're somewhere in the 2-3 range. Do some practice, take a look at the homework, send me any messages with any questions.